Hey guys, here we are. Welcome to section 2.2. We're going to be talking about limits involving infinity. In section 2.1 we talked about limits at a specific point. And in 2.2 we're going to talk about what happens as functions go off to infinity. So first we're going to look at functions as they approach infinity. We're going to look at infinite limits when our function might approach a particular value. We're going to look at what's called end behavior model, and we're going to sort of find a way to see what a limit looks like as the function would go off to infinity. So let's get started. Let's talk about finite limits as x approaches infinity. So our first question, what is the limit of the function 1 over x as x approaches positive or negative infinity? Well, here's our 1 over x graph. And as x approaches infinity, as x gets larger and larger and larger, you can see that our function is going to get closer and closer and closer to 0, but not actually touch 0. And the same thing is going to happen as we approach negative infinity. As our x's continually to get smaller and smaller and smaller, our function value is going to approach 0, but never quite get there. So the limit of 1 over x as we approach positive infinity this way is 0, and the same thing happens as we approach negative infinity going this way. We also get our function approaching 0. So our limits for both positive and negative infinity for our reciprocal function are 0. Okay, we're going to talk about horizontal asymptote. You guys talked about asymptotes in trig and pre-calc. We're going to give them now a limit definition now that we know what limits are. So a horizontal asymptote exists at y equals b, at y is some number, when the limit as x goes off to infinity of your function is equal to some constant, or the limit as x approaches negative infinity of your function is equal to that constant. So here we have the limit. This is our 1 over x function. As x approaches infinity, our limit was equal to a constant. That constant happened to be 0. Same thing here when x approached negative infinity. We got our limit to be a constant. That is when we say in calculus, that's how we prove that we have a horizontal asymptote, because the limit of the function as you run off to infinity or negative infinity is equal to a constant value. So let's find our horizontal asymptote. So what we would do is we would look at our function and see what's happening as we go off towards infinity here. And you can see that we are getting ever closer to, but not quite hitting 2. So as we approach positive infinity, we're going to get a value of 2. Same thing when we approach negative infinity here. If we continue to go out and out and out, we're still going to be approaching 2. So our limit as we go to positive infinity is 2. And our limit as we run off to negative infinity is also 2. So by our new definition, that means we have a horizontal asymptote at the line y is equal to 2. Okay, here's another example. We're going to find the horizontal asymptotes. There happen to be 2 here because as we run off to positive infinity, our function gets closer and closer to a value of 1. And then as we run off towards negative infinity here, our function approaches and gets closer and closer to negative 1. So this is an example of a function that has 2 horizontal asymptotes, both at y equals 1 and y equals negative 1. Okay, let's talk about properties of limits as x approaches either positive or negative infinity. And we talked about properties of limits as x approached a, some specific value. Well, very nicely, the same properties that apply when x approaches some a value apply when x approaches infinity. So that means, if you recall, you can add them, you can subtract them, you can multiply them, and you can divide them, of course, providing that that divisor function is not 0. And then we have another identity. So this is similar to, we had the sine of x over x as x approached 0 in the last section, and that was equal to 1. As we're approaching infinity, though, the limit of the sine of x over x is equal to 0. And again, this is like an identity. This is something you absolutely need to know on the AP exam. You would be expected to know that without your calculator. On one of my exams, I would expect that you would know that without a calculator as well. So as x approaches infinity, the sine of x divided by x, the limit of that is going to be 0. Okay, so let's do some algebra here and see if we can figure out these limits. So we're going to take the limit as x approaches infinity of 5x plus the sine of x over x. So we're going to take that function and we're going to break it up using some algebra. We're going to split that into two individual fractions, into 5x divided by x plus the sine of x divided by x. And then we're going to do some simplification into 5 plus the sine of x divided by x. So that is going to be what we're going to be taking our limit of as x approaches 0. So the limit of 5 plus the limit of the sine of x divided by x. We're going to use that additive property of limits. And of course the limit as x approaches infinity of 5 is just going to be 5. And the limit as x approaches infinity of the sine of x divided by x, we just talked about that as one of our identities, that's equal to 0. So our limit becomes 5 plus 0, or simply 5. Okay, let's look at a limit definition for vertical asymptotes. A vertical asymptote exists at x equals some value a when, as you approach a from the right of f of x, if your function runs off to positive or negative infinity, or as you approach some value a from the left side of your function, if the function runs off to positive or negative infinity there, that's when we say that we have a vertical asymptote. So if we're looking here at our 1 over x function again, as we approach 0 from the right here, our function tends to get larger and larger and larger and runs off to positive infinity. And as we approach 0 from the left, our function runs off to negative infinity. So that means that, so that means that we would have a vertical asymptote right here at the line x equals 0. Okay, so here is our function 1 over x squared. That's what this is a graph of. So the limit as we approach 0 from the right, so we're going to approach 0 coming in this way, and our function runs up to positive infinity. And then we're going to approach 0 from the left side, so we're going to go at it this way. And our function again runs off to positive infinity. So that means we have, at x equals 0, we have a vertical asymptote for this function 1 over x squared. Okay, page 73, example 5. This would be in your book if you want to read through this a little bit more closely, but this is what you'll find on page 73 for example 5 in your book. It says, for what values of a is the limit as x approaches a from the right of the tangent function, when is at negative infinity, and when is the limit as x would approach a from the left side of the tangent function equal to positive infinity. Well, this is a picture of tangent functions graph. Our window is negative 2 pi by 2 pi. So just to kind of to get your bearings here, here we are at 0, so this would be negative pi, and this would be negative 2 pi, and then this would be pi and 2 pi here. So for what values of a, when we approach a from the right side, does our tangent run off to negative infinity? Well, here's a place where I'm running off to negative infinity, and as I approach to the right of this value right here, this is where my function is running off to negative infinity. So this would be, let's see, if this is pi, negative pi, and this is negative 2 pi, well, this would be negative 3 pi over 2. And let's see, at this red line here, as we approach a from the right side, so as I come in here, my function's running off to negative infinity. So right here, again, this is 0, and this is pi, so this would be negative pi over 2. So we have negative 3 pi over 2, negative pi over 2. Here we are running off to negative infinity again as we're approaching from the right at positive pi over 2 between 0 and pi. And then the same thing right here. This value right here from the right side, we run off to negative infinity, and this would be between pi and 2 pi, would be 3 pi over 2. So we have negative 3 pi over 2, 3 pi over 2, pi over 2, 3 pi over 2, and we know, of course, this is periodic, so we could expect it to continue to happen. So it seems like it's going off to negative infinity anytime we have an odd pi over 2 value. Let's look at what what happens when we're approaching a from the left side now. We want to know when we go off to infinity. So going off to infinity from the left side is happening here, and here, and here, and here, at those very same values that when we approached from the right side, we went to negative infinity. So again, we have our negative 3 pi over 2, our negative pi over 2, pi over 2, and 3 pi over 2. So we have those odd multiples of pi over 2. And a way that we can write that is like this. We could say that a is equal to k pi over 2, where k is any odd integer. So this k is allowed to be any odd integer. So negative 1, negative 3, negative 5, 1, 3, 5. Anything that's odd, that's going to get us our odd multiples of pi over 2. And that's where periodically we're going to, the tangent function will run off to positive infinity as we approach from the left, or negative infinity as we approach from the right.